Okay, today we're going to talk about mountains and earthquakes. And obviously, the title suggests that there is some connection between these two. So we'll begin by asking the very simple question, what are mountains? I would imagine that anybody can give a very quick answer. It's a generic term that essentially you have some areas on the surface of the Earth which is higher than its surroundings. Perhaps we can learn a little bit more about mountains if we simply look at the distribution of mountain belts. If we can switch to the, yes. And a lot of this information is actually available on the World Wide Web, and in a minute we'll get a video over here. And this is simply a map of the globe, and let me see if I can arch this a little bit. Here. And you can see that the ocean basins are in this sort of bluish color, then the continents in green and yellow and so on and so forth. So actually, in the ocean basins underneath the water, there are a lot of high regions. For instance, in the middle of the Atlantic Ridge, there is a very large mountain chain going through like this. And in the continents, the stories are a little bit more complex. Some of the mountain ridges are along the edge of the continents, like the Andes in South America, and also the Western Cordillera on the west coast of North America here. But there are also major mountain ranges in the middle of the continent. This is Eurasia. India is over here. There is a major mountain system over there. So just by looking at the distribution of mountain ranges, don't give us a very clear answer as to how these mountain ranges are formed. So now we can look at the earthquakes and ask for the same question, what are earthquakes? How many of you have actually experienced an earthquake? Anybody? Okay. Could you tell us what you felt?
It wasn't a very big one. My mom just told me.
Okay, but it lasted for less than a minute. Okay, so
more on the second scale.
Okay, so it lasted for seconds to minutes. And are we experiencing an earthquake right now, do you think? No, we don't feel anything. So this is a characteristic of an earthquake. It's actually an event that happened at some point in space and time. It's not a tangible object. However, we do have very good records of earthquakes, the time and the location of earthquakes, and we can look at those. And what I'm going to do is to show a computer simulation. It's actually the real data. We're going to plot the location of earthquakes on a map, and the time sequence is a compressed time sequence. We will try to compress years, about 30 years of data into a frame of maybe 1 minute. So this is, the sequence are correct, but everything is played much, much faster. So I need to get out of this. The program is also running on this computer. To switch here. Okay, so in a sense, it's like a little movie here. And let me see, I need to do this. Okay. Okay, now we're going forward in time. Over here, fairly quickly, this is a map of the world, and the dots are the earthquakes. The size of the dots represent the size of the earthquakes, but pretty soon a pattern is emerging in that along the mid-Atlantic ridge, where we said there is a major mountain range, the earthquakes are beginning to line up along the same place. For instance, on the west coast of North and South America, you begin to have a line of earthquakes as well. In this region, the Himalaya and Tibetan Plateau region, you also have a lot of earthquakes, and there are also other belts of earthquakes. We can look at this in a smaller scale. Let's look at the Northridge earthquake, which occurred about 2 years ago near Los Angeles. Los Angeles is about over here, and this is the San Fernando Valley. You're hearing a little tune here. This is actually the time sequence of earthquakes happening, and there is some pattern in the time sequence, although we can't quite make out what it is. So I'm going to get out of this. Come back to our slides here. The point is that in terms of the location, there's a very good correlation between the location of earthquakes and the major mountain belts in the world. So perhaps it's not surprising that these two are somehow related. The study of earthquakes can be traced way back to almost 2,000 years ago, back to 132 AD in the Han Dynasty in China. And at that time, a fellow named Chen, who was the director of the Royal Astronomical Observatory, devised the first instrument to measure the vibration of the ground and therefore study the earthquakes. Almost 2,000 years went by between Chen's time and the beginning of the century. We didn't really know too much about how earthquakes occur. After the 1906 earthquake in San Francisco, there was actually a large rupture in the ground to the north of the city that was studied in some detail. And in particular, this fellow named Reed, around 1910, published a sequence of papers and really figured out, at least in general terms, how earthquakes work. And I would switch on this slide over here. The first slide just shows a mountain climber. We lift off. Yeah. Okay, thank you. This is the distribution of mountain ranges we have already seen. This is just a damage of the caused by the Northridge earthquake. This was a parking garage in the California State University in Northridge. This is the distribution of earthquakes. Again, we have just seen the computer simulation over there. This is what I want to get to. Let's say around 1850, 50 years or 56 years before the occurrence of the 1906 San Francisco earthquake, there was a fence laid down in a farm. And gradually, over the course of 50 years, people realized that the fence was actually bent like so, as if the two sides of this block are trying to move relative to each other in the sense indicated by these arrows. And right after the earthquake, a rupture was formed on the ground, and this is known as a geological fault, simply a rupture and along which two sides of the rock move. And what happened to the fence? Of course, the fence was snapped along with the ground. However, the two sides of the fence are again straightened out. It's no longer bent. So whatever deformation was stored in this piece of rock was all of a sudden released by this earthquake, and then the deformation was restored. And this is known as the elastic rebound theory. Essentially, this piece of rock was deformed, then it bounces back to its original shape, and along with it caused the vibration of the ground and causing an earthquake. And we can do this sort of kitchen experiment with a yardstick. I'll just push one end of the yardstick against the side of the table, and now I'm going to move in this direction. Because there's friction between the end of the yardstick and the table, so the end at the moment doesn't move, but the yardstick actually is now bent. If I continue to move, eventually there's too much force between the end of the yardstick and the table, then the yardstick simply snaps back. And this little sound is an earthquake, and the straightening out of the yardstick is indeed the elastic rebound. And soon after that, people started working on mathematical and physical models of earthquakes. And turns out, again, we can do this little experiment here. It's going to be a little bit hard to see in a large room. Say, this is the eventual rupture on the ground. Los Angeles is here, San Francisco is there, and the two sides of this geological fault will try to move in a sense indicated by these large arrows. And as I force the two sides to move, what will happen is, in addition to the slip along this surface, the ground actually warps up and down in a regular pattern, and this is what I'm trying to produce here. It's going to be somewhat difficult to see. But the places marked up actually warped up, and then followed by a down warping region, again up warping region, and down warping region. So you end up with this pattern of up, down, down. And these kind of distortion of the ground is actually propagated as seismic waves to long distances and can be recorded at faraway stations. And this theory was developed in the 20s, but it didn't meet much success. Turns out the reason is that we didn't have very good observation. The ancient seismic instruments weren't very well calibrated, and the communication between the stations weren't very good. Beginning at the 1960s, it's for the first time there is a standard set of instruments distributed all over the globe, and all the instruments are made the same, and they're very well calibrated. And all of a sudden, a very clear picture began to emerge. And we can see the pattern of the ground, that it either goes up or goes down, and it's a regular pattern. I need to switch to the workstation again. Because in the past 10 years or so, we can actually look at real seismic data over the computer network as the earthquakes occur, and I was trying to show an example here. There is a consortium for the study of seismology, and the University of Illinois is one of its founding members, and you can access this homepage through the World Wide Web. And I'm going to call up a map of the world here. What happens is that there is a set of stations distributed around the world, shown by the little black dots here. There is communication between these stations and data centers distributed around the world through telephone lines or satellite links. As an earthquake occurs, occurred, then a computer would send a signal to this station and say, send me the data that you just recorded to the data center, and then we can dial up to the data center like we just did and get the real data from this earthquake. What this map shows is an earthquake near Iran, and the paths of seismic waves in map view to different stations. So there are about 30 or 40 stations that will report data very quickly back to us, almost in a real-time situation. I'm going to go back here, and this is just a sample of the data. What you're looking at is simply a list of the stations and some other information regarding the station and the earthquake. What we're going to do is simply to look at some actual records of the ground motion. On the horizontal axis is simply time, and on the vertical axis is the velocity of ground vibration. There are three traces representing three directions: vertical up or down, north, south, and then east, west. Let's look at only the first trace, and you can probably see that the ground was at rest. Then as the earthquake wave arrives, the ground actually moved downward. This is a station in Europe. Let's look at a station in Australia. The same kind of setup. These wiggly lines are called seismograms. Again, look at the first trace only. The ground actually went up when the seismic waves arrived. So what we can do is essentially look at the up and down patterns for a large number of stations, and then somehow project this information back to the location of the earthquake. This would actually tell us about the orientation of this geological fault. Nowadays, things are more sophisticated. What we can do is not only look at the up and down patterns, but actually simulate the entire ground vibration during an earthquake. And this is just an example. Again, these wiggly lines are those seismograms. This is a fairly complex earthquake, but we can match almost wiggle by wiggle. There are actually two curves here: a solid curve, which is observed, a dashed curve, which is what we calculate. And if you can't see the difference between those two, that means that we did a very good job. So what we can learn from this kind of exercise is, first of all, the depths of these earthquake faulting. This earthquake occurred at a depth of 640 kilometers beneath the surface. Also, the orientation of this geological fault here. In addition, we know the sense of slip across these faults, and also how large an area of the fault that actually slipped. So in the 1960s, this kind of information contributed greatly to the development of the plate tectonics theory. This is a very fascinating piece of history of science, but we don't have time to go into it today. Just to summarize the results, essentially what we found is that the outermost layer of the Earth is known as the lithosphere. It's just a layer of rock that has some mechanical strengths, but it's not an intact spherical shell. It's made of a mosaic of many pieces. Each of these pieces is known as a tectonic plate. So essentially think of the Earth as some sort of a jigsaw puzzle, except those pieces of the puzzle are not stationary. They're moving constantly relative to each other, and the speed varies between 1 to 100 millimeters per year. 100 millimeters is about 4 inches. Our fingernail grows about 2 inches a year. This gives you an idea of how slowly really the plates are moving. If we look at North America, it's over here. Chicago is here. Champaign somewhere down here. We're sitting in the middle of the North American plate. How do we know the boundary of these mosaic or jigsaw puzzles? Essentially, these are the places where earthquakes occur. How do we know the sense of relative motion, say, between the Pacific plate and the North American plate? Well, we can look at the sense of motion across the geological faults by looking at the pattern of ground motion associated with earthquakes. And the beauty of plate tectonics is not only that it works, it's really very, very simple. Turns out there are only 3 types of boundaries between lithospheric plates or tectonic plates. The first type is known as the divergent plate boundary, where you create new lithosphere, and the 2 plates move away from each other, hence the name, the divergent plate boundary. What often happens there is that in addition to earthquakes, we have volcanoes, and these volcanoes essentially are made of molten rock, and they simply ooze out of fissures of the earth. This is how Iceland was built. It's not a violent eruption. And this essentially explains why there are mountain ranges smack in the middle of the Atlantic Ocean, for instance. Well, if we keep on making new lithosphere, then the Earth has to be getting bigger and bigger, and that's not really possible. So what has to happen at the same time is that we recycle some old lithosphere back into the interior of the Earth. And these recycling centers are called the convergent plate boundaries because 2 tectonic plates move towards each other. And along these convergent plate boundaries, again, we have earthquakes. We also have volcanoes, as shown over here. These volcanoes are built a little bit different. They're much steeper, and often they have violent eruptions, like the eruption of Mount St. Helens in 1980 belongs to this type. And also, this is where you find a different type of mountain ranges along the convergent plate boundaries, and that's something that we're going to talk about later. This would provide an explanation for mountain ranges such as the Himalaya and the Andes. So finally, there's a third type of plate boundary. The lithosphere does not get destroyed or created along these boundaries. Essentially, 2 lithospheric plates slide by each other subhorizontally, so you don't build spectacular mountain ranges, but they are earthquakes, and this shows the famous San Andreas Fault on the west coast of California and the occurrence of the Loma Prieta earthquake south of San Francisco in 1989. So the basic cause of mountain building is simply the movement of tectonic plates, but we can look into this in a little bit more detail and look at the basic physics of mountain building. I need to move over here. There are really only 2 or 3 important physical principles involved in mountain building. The first one was discovered in the 18th century. Let me advance this screen here. When the French started measuring the shape of the Earth and distance between major cities on the Earth, Pierre Bouguer realized in around 1750 there's something very strange happening to his measuring instruments. He was next to the Andes, and he realized that when he hung his plumb, it doesn't go down directly to a vertical. Instead, there's a minute angle between the plumb line and the vertical. It's only a fraction of a degree, but this is known as the deflection of the vertical. Bouguer said, maybe what happens is because the Andes are sitting right over here, so there is some excess mass which is essentially shifting the position of the plum here. And you probably know the Newton's law of gravitation, which simply says that the gravitational force between two objects is inversely proportional to the distance between these two and proportional to the product of the mass of these two. And this is known to Bouguer. So he said, well, this must be the answer because I know the distance between the plum and the center of the mountain, and I can estimate the mass of the mountain by looking at its shape and knowing its density. But actually 100 years went by, people accepted this until they actually did the calculation in the Himalayas. The famous Everest noticed the same problem in the Himalayas, this deflection of vertical. He actually did this calculation and found out that if you follow the reasoning proposed by Bouguer, the expected deflection of vertical is almost twice as large as what you actually found. So something must be really wrong. Well, is it the Newtonian law of gravitation or something else? A fellow named Pratt proposed the following scenario. Said, well, what really happened is that indeed the mountain as we see it above the Earth's surface represent some additional mass. However, the mountains have some sort of a root, very much like a piece of wood floating in water. You see the tip of the iceberg, so to speak, but there is a much larger root beneath the surface of the water. And because if you think of an analogy, let's say the Earth is made of water and the mountains are simply blocks of wood, the water is denser than wood. So the root actually represents a so-called mass deficiency. It's slightly less dense, therefore compensate for the excess mass that you have at the top of the mountains. And if you did that kind of calculation, the expected deflection of vertical is very close to what you have observed. So the first conclusion is that the mountains are sort of like wood blocks floating in water. They have roots. Does that make any sense? Maybe, maybe not.
Yeah.
Yes? Okay. Well, stomp on the ground. The ground doesn't give. Does the Earth behave like a fluid, like a liquid? Well, we can go out in the field and see this. This is simply the analogy I have just discussed. Higher mountains and lower mountains and so on and so forth. So there are several questions here, and I would switch over here to this camera. See if we can get this working. This one. Okay. Well, I have two pencils here immersed in water, a white pencil and a yellow pencil. The question is, which pencil is longer? Are they the same length? Or maybe one is longer, one is shorter? Anybody see any ideas? Think of the white pencil as a very tall mountain and the yellow pencil as a very short mountain. Any suggestions? Well, there are only three possibilities, so we can make a guess. They're the same lengths. Everybody agrees?
You can't really tell.
You can't tell. Well, yeah, that's a possibility. Well, this is relatively simple because we can simply take the pencils out of the water, and the white pencil is actually much, much longer than the yellow pencil there. And this is the idea of this slide. If you have a taller iceberg, essentially the iceberg has a larger root. But still, this hinges upon the assumption that the Earth behaves like a liquid, and this is something we like to examine. And if you look at this picture here, indeed, the rock layers actually warp, and they have some characteristics of fluid. So this is what we actually see in the Earth. On the other hand, if we stomp on the ground, the Earth does not behave like a fluid. So something must be controlling this type of behavior, and this is what we'd like to explore. So I'm going to need a volunteer because I have pieces of rocks here. Now they're relatively flat. Okay, I'd like you to somehow make this rock layer into a shape like that. Do you practice Taekwondo?
No.
No? Okay.
I don't think it's going to work.
Well, try it anyway. It doesn't work. What did it do?
It didn't do much.
Didn't do
I could
much.
break it, I suppose, if I hit it against something, but that wouldn't do it.
Okay.
It wouldn't bend it.
All right.
I suppose
Okay.
maybe if you did constant pressure for a long time, it would change the shape of it.
Okay. All right. Thank you. Well, we need someone else. One suggestion was that we apply more force because he did not practice Taekwondo, so he couldn't break this. Anybody else like to give it a try? Another volunteer, please. Jenny. Here, put on this safety glass. Okay, we have a hammer for you, so try to apply more force. Thank you.
Okay.
Well, indeed, the rock simply shattered. She broke it, but it didn't turn into a fluid or deform in the way that we want. So what is going on? Well, we have some silly putties here, and we will try to use these as an example. As we all know that you can really deform these silly putties very easily. In fact, this morning I made all these into round balls. Now they're all flat because they're just sitting here. I have another ball here immersed in ice water. I need yet another volunteer to try to squeeze this silly putty and see how it feels. Yes, please. I'd like you to come down here and compare how easily you can deform this cold one or this warm one. See which one is easier to squeeze. This is a warm one. Is that easy to squeeze?
Yeah, it's pretty easy.
How about this one?
This was harder.
It's hotter when it's cold. Yes. All right. So that's one thing. It's very important. Seems like the temperature of rocks or material in general has a lot to do with whether the material is hard or weak. Thank you. Well, next one is somewhat a different bend. Again, I'm going to need a volunteer. Also need you to place some wagers on this. What will happen if I drop this on the ground or smash it really hard on the ground? You think it's going to what?
It's deforming now.
I heard something, if you smash it, it may fall flat on the ground and sort of flop. Some people say that it may bounce, spread. We have all kinds of answers. Well, there's only one way to find out, right? To try it. So someone wants to try this? You, sir, maybe? He wants to do it. Very good, yeah. So I hope you have all placed your wager. Just try it if you throw it on the ground. Oh. We've lost it. Wow, we have another one. Here. You won't be charged. Well, you think if we throw it really hard, it's going to fall flat on the ground?
I guess.
You guess? So try it as hard as you can. Lost another one. All right, thank you. So what's going on? I mean, I can squeeze this thing into any shape I want relatively easily, but if I throw it hard on the ground, it actually bounces like a rubber ball. What's the difference between these two? Yes?
The amount of time that you're spending. If you instantaneous force, it doesn't deform, but if you do it slower, then it deforms.
Yes, actually you sort of gave the answer when you try to bend the rock already. And that's precisely what's happening. When I'm doing it slowly, the material behaves relatively weak. If I want to deform it very fast, like throwing it on the ground, it actually behaves as a very strong material. And this is indeed what's happening. You can verify this in the laboratory. When we try to, say, bend this piece of rock, it actually bends a little bit. It's just the amount is so small that we can't see it. The change in length is less than 1%. And when we release our hands, the rock bounces back to its original shape. And we say that it's doing elastic deformation, very much like stretching the rubber band. It always comes back to its original shape. If you apply a lot of force and the material is relatively cold, it goes through the so-called brittle failure. That's when Jennifer smashed this piece of rock. It simply broke. It did not warp or flow. When temperature is high, the material would appear to be weak, and it will actually behave more like a liquid. So when the material is brittle, wrong direction. You create these faults or fractures. This is an aerial view of the famous St. Andreas fault. This is the fault. These are gullies formed by streams. You can see that this particular channel is offset by this fracture over here. This happens near the Earth's surface where the temperature is relatively low. When the temperature is high, the material behaves more like a fluid, so you have these sort of flow-like structures over here. And also this takes a long period of time to form. If you try to do it quickly, like what we're doing now, right away, it won't happen. It takes a long time. So the property of the material depends on its temperature as well as how fast we want it to deform. And these are the important points here. And the fancy word for this is that it's going through ductile deformation, and the result will be called folding or simply flow. And this is very sensitive to the temperature and as well as how fast we want the material to deform. So now we can talk about a specific mountain range, the Himalayan Tibetan mountains. The first question we would ask is, why would you even care? Mainly because this is the most spectacular mountain range on the Earth. This is a view from satellite. These are the snow-covered peaks in the higher Himalaya. it's several hundred kilometers in width and almost 3,000 kilometers in length. If we come down to the ground, this is how the higher peaks look like. There are glaciers over here. And if we look at a topographic map of the Himalaya region, it's quite spectacular. The different colors simply shows the relief. The scale is over here, so the average elevation here is about 5 kilometers. Himalayas is over here, and this large mass here is the Tibetan Plateau behind it. And in fact, the area covered by this reddish color is larger than the state of Texas over there. 80% of the world's surface with an elevation over 4 kilometers or higher can be found right here in the Himalayan Tibetan region. The black dots here are the earthquakes that occurred in this area in the past 30 years or so. So there are a lot of earthquakes here attesting to the fact that this is an active mountain range. It's being deformed. And what we can do, of course, is to use these earthquakes and understand how these mountain ranges come up. But in terms of the very basic cause of the Himalaya, we can look at the slides over here. From plate tectonics, we have an idea of the history of plate motion between India and Asia. Say 60 million years ago, there was actually a vast ocean between India and Asia. And we have one of these convergent plate boundaries where we recycle this ocean floor. So over time, this entire ocean floor was actually consumed. And then the two continents meet, and then we say they collide because of buoyancy of the outermost layer known as the crust. They don't want to go down because they're buoyant, so this system is choked right over here. And this happened about 40 million years ago. When the system is choked, the plates still want to move relative to each other, but the crust cannot be subducted. It wouldn't go down. So what happens was actually a series of very large geological faults down to a depth of about 50 kilometers occurred on the northern edge of India. And essentially this stack is broken off from the northern edge of India, was pushed southward on top of the Indian continent. And this process occurred more than once, at least 2 times in the past 40 million years. So by stacking up these broken pieces of the lithosphere, you have created the highest mountain range on the surface of the Earth. And on the ground, you can actually observe this. This is just a cross-section showing the different geological structures along the Himalaya, going from India to the Tibetan Plateau here. I'm just going to show you very, very quickly a few slides that I took along the Himalaya. First, we're going to look at this area, and then we'll move into the higher mountains and see the kind of deformations that's going on over there. Now we're just standing over here, the foreland region, looking back at the mountains. The Himalayas are in the back over here. This is actually a basin, rocks that were washed off by river and glacier from the Himalaya is deposited over here. So there's actually a little bit of flexure. The Indian lithosphere actually went down a little bit because of the weight of the mountains. Then the sediments are collected in this little puddle over there. And then as you walk into the interior of the mountains, you see evidence of folding. That's ductile deformation we described. It's a little bit hard to see because things are folded up so tightly that originally horizontal layers are now doing this. And that's in the center of the slides here. That's how you have these structures. It's probably a little bit hard to see from the back. You also see evidence of geological faulting. There is a fault running through right about here. The rocks on top of the fault is very different from the rocks near the bottom. And of course, we have a lot of earthquakes. And for instance, we know there's a fault over there because there was a very large earthquake occurred at a depth of 50 kilometers or so in 1988. And we can look at the seismograms and determine the orientation of this earthquake faulting. The other things shown in this picture, for instance, there are some blue lines shown over here and here at great depths, something like 50 kilometers or so. There are no earthquakes there, so how can we find out the structures in that area? Turns out another way of using earthquakes to understand the Earth is to look at the different seismic waves and to probe the interior of the planets. And people have actually tried this to understand the internal structure of stars, such as our sun as well. We're running a little bit low in time, so I'm not going to go into the details of this, but I do want to show you an animation of how the internal structure of planets affects the propagation of these waves. And you can think in the reverse order, that is, how we can use these propagation waves to understand the internal structure of planets that we cannot see. So what's going to happen is that we're going to see a cross-section of the Earth, just a slice through the middle of the Earth. Then there are several earthquakes we can pick, and we can choose an earthquake and let it go and see how the waves actually propagate into the interior of the Earth, then come back to the surface. And also we're going to show seismograms, these history of ground vibration at some selected stations. So you will see that the wave shapes you see at these different stations, and they correspond to different ways of bending and reflection of the waves. So we have a choice. Which earthquake do you like? You like the Kobe earthquake in Japan? You like the Kobe earthquake? All right, right here. So let's try this. I'm going to pause it here simply to explain what's going to happen. This is a map view of how the front of the waves propagate. This is a cross-section of the Earth. You see different layers in the Earth, and we found out these layers by precisely looking at these waves. Up here, there are seismic stations. Seismograms are going to show up here. At the beginning, they're flat because no waves have reached that station. As a major vibration occurs at a particular station, you'll hear a very faint click indicating some particular wave has hit the station. These are the distribution of stations: Harvard, Massachusetts, for instance here, College, Alaska, and this is actually Taipei, Taiwan, my hometown. And Kobe earthquake is over here, Australia is over there, and this is the Pacific Ocean, College, Alaska is over there. So don't worry about any of the details. I just want to give you a feel of how these waves propagate. So let's get it going. You see a wave expanding from here, and pretty soon Taipei is going to receive this earthquake wave right here. And then this wavefront hits some boundary inside the Earth, gets reflected, now it's going up again. In the same time, the waves spreading out in different directions. And pretty soon the picture gets fairly complicated as different stations begin to see the ground vibrations. Now you see some very large vibrations in Taipei, and Harvard is just beginning to pick up some relatively faint ground vibrations. And look at all these wavefronts go through the inside of the Earth because of the complicated structures there. And it may surprise you, for instance, after the Bolivian earthquake in 94, the earth actually shook for several days, although the period is so long, it goes so slowly, we don't feel it, but it's faithfully recorded by all these instruments. So the whole earth actually went like this for several days. Okay, I'm going to get out of this and get back to this picture. We don't have time to go into the details, and I will just quickly conclude here that the basic cause of both earthquakes and mountain building are the motion of the tectonic plates. And in fact, we can use earthquakes to study how mountains are built. And there are several features that we know very well about mountains. One is that mountains have very deep roots, and the fancy term is called isostasy. This is essentially like wood blocks flowing in water. The reason that the earth sometimes behaves as a liquid is because, number one, the temperature is fairly high at depths. Number two, geological processes go very slowly. Typically, it takes millions of years, so the material would appear to be very, very weak. And the Himalaya mountain ranges are built by the collision of Eurasia with India. Because the crustal blocks don't want to go down, what happens is that you broke off slices of the Indian lithosphere, stack them up, and that's how you have these really high mountain ranges. We can use the seismic waves to probe the interior of the planet, including to map out the deep roots of the mountain ranges. And a very nice feature about earth science in general is that you can combine field work with laboratory work. For instance, you can visit the Himalaya or the Andes for that matter. Thank you very much.